welcome to all of you, and welcome to my colleague, Professor Sir Andre Geim. And we'll be chatting in a few moments about graphene and how it's changing science and technology. I'm sure you will have noticed that the University of Manchester is celebrating its 200th anniversary. We have a lot of anniversaries this year. It's also 20 years since the two universities in Manchester came together to form the University of Manchester. And just a few days after that formation, the groundbreaking paper on graphene was published, demonstrating the remarkable properties of graphene. And then it's also timely because today is the announcement of the Nobel Prize for Physics. And of course, 14 years ago, on, I believe, the 5th of October, it was announced that Andre and Kostya Novoselov had won the Nobel Prize for Physics. And I was honored to be able to attend the ceremony. So lots of celebrations and very timely, and thank you, Andre. So at the time, graphene was quite quickly called a wonder material. Why was that? Just explain to those people who are not familiar what is so amazing about graphene and why people had speculated about it for so long and yet not been able to demonstrate it.
To be honest, it was not at that time, if I remember correctly, and I do remember correctly, the word wonder material came in 2009 in my review paper as a single author in Science review paper where I called it wonder material. Before that, people, especially journalists and politicians, try to call it magic material. And as a scientist, I don't believe in magic, so I have to invent a better, more accurate word for this. And wonder material comes for a reason. It shows so many properties different from other materials no one could expect, and it continued, you know. Typically, when someone finds something interesting, a group of academics all over the world just budge into this area, and after 2-3 years, everything is done, essentially. This material proves itself long-lasting material, probably unlike any other material we know or any other research area, I would say, maybe except for quantum physics, that lasted for 20 years. So wonders continue. Every 2 or 3 years, some news. Everyone thinks that everything is done. Some news comes out, like, I know it's very specific subject in science, but there is a lot of new excitement appears every 2-3 years when no one expected.
So I remember in one of the press articles, you illustrated the amazing properties of graphene by saying a tiny amount of graphene, when it's spread out, could cover 5 football pitches. And then in Manchester, that's how we measure things, in football pitches.
Yeah.
But you also described that I think you could put a pencil on a sheet of graphene and stand an elephant on the pencil and it wouldn't break the graphene.
Yeah.
Is that correct?
That scientific paper was published exactly trying to estimate. It was tongue-in-cheek, a little bit paper, but it's scientific with proper estimates. Not my paper, but it was like that. And that a frog can make a gammock, but it was an invention of Nobel Prize committee. They decided to check out whether this pencil exaggeration was correct or not, and they put a frog on, I think, square meter of graphene and say it could serve as a gammock.
Okay, so it was true. And by the way, those of you may be aware that Andre also has another important achievement relating to frogs, which is, of course, the Ig Nobel Prize for levitating frogs in a magnet. But we'll leave that for now. But then these properties kept emerging. I mean, it wasn't just its strength, it's incredibly thin. It was electronic properties, it was heat properties, it was reflectant, conducting. It seemed to be almost everything. True?
That's absolutely correct. So the Nobel Prize was given essentially for a very small segment of a huge area graphene started. The area could be called two-dimensional materials, and their variations, but it's a shorthand for this area called graphene, and Nobel Prize committee focused on electronic properties of graphene, which essentially were so unusual, especially they allowed to mimic many phenomena which occur only in relativistic quantum physics, which means near neutron stars and in particle accelerators. So yeah.
And is it true that it has the potential to replace silicon in electronics and lithium in batteries?
And in what?
Lithium in batteries.
Two answers. About silicon, it was a lot of speculation about graphene instead of silicon. Probably not my personal opinion, although I can't exclude this. On the other hand, graphene-like materials, two-dimensional semiconductors, there are several of those now very popular latest sisters and brothers of graphenes. They're considered by semiconductor industry as the next material base for electronics. I also a little bit doubtful about this claim, but what is certain then, if we are talking about flexible and transparent and kind of wearable electronics, those graphene-like materials have a very good chance. They're not as developed as graphene yet. As concerns your question about, your layman question about graphene in batteries.
I'm just a biologist.
It's already there. So first of all, it was always there because graphite is the basic material for lithium-ion batteries. One of electrodes is just pure graphite. And when lithium goes inside graphite, it splits graphite into individual graphene sheets. And this is how it works. More recently, graphene has become even more in lithium-ion batteries and also more in other kinds of batteries, especially lead-acid batteries. Industrial companies add graphene as an additive into their mixture of how they make electrodes and so on, and it improves properties of those batteries by a few percent. Some people call it graphene batteries for a hype. Some more serious companies just don't mention it. It's within the recipe. I think most batteries, if you have an electric car, there is graphene there. It's majority of batteries come from China, and China is very intensively using this as an additive, but it's a minor application.
So there was also, once graphene people became aware of its properties, there was what you described to me at the time as a lot of snake oil, because people were selling graphene and making a lot of money for things that were not graphene. Was that harmful to the field? I remember a few of them.
But there are two sides of this story. One of those making a lot of money, my PhD student who runs now a company called Graphene Industries, is the longest surviving company in graphene business, I believe, starting in 2006 or even maybe a little earlier. They sold for probably about 10 years tiny pieces of graphene, which some in this audience have seen under microscope, including your lordship, David Willits, and those tiny flakes were sold for up to £5,000 for something which is easily fits in the cross-section of your hair. It was a lot of money for PhD students, and when people complain that this stuff comes so expensive, I always replied it's very cheap per atom. On the other hand, okay, on a more serious note, speaking about applications, it's the standard issue with in industry when something new comes out, whether it's graphene, artificial intelligence, quantum computing, whatever, there is a hype around this one, natural development of things, then it's value of disappointment, as we all know, and after that, things start developing recently. So yeah, somewhere 10 years, 15 years ago, it was all hype. And many companies got busted, and now there are companies who are start doing decent thing, and graphene is in their portfolio, although it may be not called graphene company, but it's just using it.
And now you can make tons of it, literally tons. It's possible to make huge quantities now.
I don't know the exact numbers, but I would be surprised if it's less than many dozens, if not thousands, not hundreds probably, up to hundreds of tons every year is produced, not only in China, Italy, big producer, also UK, there are some companies producing this. Usually, most applications come as a powder application. There is also technology developed to make it in square meters and so on. People can make it in square kilometers quite easily and sell it, but that hasn't found its applications yet.
So when you won the Nobel Prize, Howard Bernstein, then leader of Manchester City Council, and I wrote to the Chancellor, George Osborne, and said, two of our staff have just won a Nobel Prize. Will you give us the money for a building? Which he did, indeed, although Andre decided we should ask for a little less than we were figuring. But we still got a significant sum of money. And then I remember very well the conversation Andre had with David Willits, who is here. And David was frustrated at why it would take several years to complete this building. Andre's answer was, we don't buy this sort of equipment in a supermarket, which of course we don't. But then things really started to take off. And I remember, Andre, many conversations we had and the frustration that a lot of big companies literally shied away from graphene. It was too disruptive. They just didn't know what to do with it. And that went on for some time, didn't it?
It's natural things how it's happening. It's not like writing a computer code and within a few years, if it's successful, you become a billionaire, which happens in the history many times. With materials, it takes a lot of time. First, you need to investigate the material, get all the properties, and all is limited. You know, it's still Scotch tape technique, as we initially isolated graphene. Hundreds, thousand groups around the world use the same technique, but it's not industrially viable. Then industry eventually hear rumors, hearsays about how wonderful material is, and starts applying this material, find it either useful or completely useless, and then change their opinion. Let me give you kind of a case study, how it's usually goes. People heard about graphene, it's a black material, would be a good additive to something. And one of those cases, which probably was already counted for 15 years, maybe slightly years, was additive to tarmac, asphalt, okay. I thought this is hype because it would be never enough. It's too expensive even when you make it as a powder, but people tried. So they make in the lab formulations and so on. Then eventually someone persuaded to put graphene in tarmac on a stretch of the road near Oxfordshire. National Road Agency or whatever it's called supported this project. So how many years does it take to try? I think tarmac typically serves 6 to 10 years. So the numbers which came out from this project, that it increases the price of tarmac by 20–25%, and the durability increases 2.5 times. Even if you have 6 years serving roads, then to prove this number you need 15 years of studies. So they probably somehow aged or did some other tricks. You need to make sure that it works. So it's not something which is proven or bought from supermarket with the recipe there. And there are so many recipes, and people gradually move trying to prove this. And just months ago, I was in Italy, and there is a company, Director Plus, an Italian supplier, one of those massive quantities of graphene. And then now, next year, 2025, it's scheduled to cover with this graphene-enhanced tarmac to cover motorway, all the motorway between Turin and Milan. Yeah, so
it happened in the end.
That's how it's happening, and this is why it's happening slow. And I'm surprised that it's happening so fast, because it requires time to make sure that it works, and it requires time to find the formulations, and I'm sure that it's not the best possible formulations which they use now.
Yeah, people often forget, don't they, that silicon was 40 years, probably until it really, graphene's, 20 years old, I suppose, in terms of the public's eye or industry's eye. But now, I mean, initially, the sort of low-hanging fruit applications came through. Sports equipment was one of the first, wasn't it? Running shoes and tennis rackets and squash rackets. But now there are some more ambitious applications coming through. Which are the ones that you think are at the forefront at the moment?
Nancy, we still, it's applications. What I think the session is called Change in Science, not Application Technologies, and we haven't
Go on, how's it changed science then? How has it changed science?
About science. So let me tell you a story, okay? That's first of all, because I'm kind of, my Nobel Prize was for physics, not for applications of property development. So it's not my area of expertise. So once I was on a boat trip, and we watched dolphins. Very unusually, they kind of decided, the school decided to play with humans, and they were very close to the boat and didn't allow to touch them, but were just close to touch or a bite from the boat. So everyone leaned over the boat, and it was, you can imagine, magic moment, mesmerizing that it's happening, and everyone was at awe for a few minutes. And then a little boy behind shouts, "Man, can we eat them?" So that's, it's kind of, especially in early days when graphene came in a very small flakes and on a pencil trace, okay, we we were studying those wonder properties of materials people haven't seen in condensed matter before. And people pushed and pushed, okay, can we eat it, okay, and what's useful about this material? And as I said, I'm not responsible for applications. I try my best to push my PhD student to do to run companies and open the companies, and there is a big initiative in Manchester, thanks to chancellors and vice chancellors, to support this initiative, Ali Harari Award and so on, which is kind of, I believe I was at foundation of this award. And it takes time and with applications, but in terms of science, it's not the science of graphene completely done. It's probably no longer a very deep gold mine, but small gold mines appear every couple of years. We know that 5 years ago, graphene has become superconducting. It's a big hype in the community. A lot of interest still continues. This year, it appears so-called anomalous fractional quantum Hall effect, which is kind of many-body quantum condensed physics phenomena, probably completely very far from from interest anyone in this audience, but it's thousands of people now try to understand how it works. I would be not very much surprised if graphene, and especially two-dimensional materials, get another Nobel Prize or two in the coming decades. So rich the area is. There are people who believe in this community, and other people believe that their belief is reasonable, that they are candidates for the Nobel Prize within this area. Science, if you look at condensed matter physics, semiconductor physics, material science, all over the world, over the last 20 years, it's so much changes. You hardly find a university, even in developing countries, which are not doing graphene or two-dimensional materials. Many, we work at the universities, and many people know that some areas of research, 50, 60, sometimes 100 years old, there are only few people who are interested in those research areas, and they are dying. So graphene kind of changed landscape. Many areas were just abandoned, and graphene and graphene-like materials has become very popular. It's perpetuated not only condensed matter physics, which is my area of expertise, but into all material science, into chemical engineering, into biology. Just a couple of months ago, I met another president of Tsinghua University, a new president, and he is neuroscientist. I thought the talk about graphene implants was a complete hype and BS, but apparently not. It's the best electrodes you can make for brain transplant, so it's very likely if we have some kind of neural links, which some people do have.
The first graphene-coated implants went into patients in Manchester just a couple of months ago.
I didn't know.
Salford.
It's impossible to know all these transplants, but graphene Neuralinks are there.
So I'm going to ask you one more question. We did start late, so I think we're allowed to run a few minutes late, but I don't want to take too much of the next session's time. But my last question to you, before I'll see if there's a few questions from the audience, is looking back 20 years or 14 years, what would you have done differently? Is there anything you would have done differently with graphene? And should the university have done anything differently?
Yeah, okay. You wish for reincarnation, yeah. The second part of the question about university, certainly we were under a lot of pressure, especially from the parliament and ministers and politicians to do a lot of patenting, and somehow and journalists, they like to publish, and newspapers saying that Manchester have much less patents than China. And why it is so? Why didn't you patent it? There were questions in the parliament asked, and Nancy was pestered extensively about this. So we were under pressure, and we spent probably £1 million or something like that, maybe even more, on useless patenting, which I always, even at that time, was against, but eventually, gave up under the pressure, so our papers were turned into the patents. No one used. It's a very subtle instrument, and until you have a commercial product, in summary, to summarize, it's better not to do any patenting. I remember I even wrote an opinion piece in Financial Times after Nobel Prize, but it still doesn't change an opinion, of journalists and politicians. They still believe that patents is somehow an indicator of the progress of the universities and their contribution. It's a complete and utter nonsense, and this part is at least one element which I would completely abandon.
Thank you. So,
Not your fault.
Thank you, Andrei. Yeah, we had many a discussion about this. I'm going to throw open to just a few questions, because we did start a bit late. If you put your hand up if you've got a question for Andrei, not for me. Anybody want to? Hang on, there's one there. Yes, over there. Thank you.
Thank you very much. Phil Beatty from Times Higher Education. We did refer to the levitating frogs and the Ig Nobel. I'd really like to hear more from you, Andrei, around the importance of fundamental research and how important it is to have the freedom and the playfulness in research, not to seek short-term applications, but to have those profound changes. How important is it that we fund fundamental research and allow experimentation and playfulness in science?
Yeah, this is one of my windmills which I was fighting for, I don't know, more than 25 years, importance of fundamental research. Some of ministers came to my office, and there is a picture, a copy from Picasso, Don Quixote, and they ask, "Oh, you like that? What is there?" I think that's kind of me. Sancho Panza, it's Kostya, and these windmills are you, minister. It's a battle all the time.
Something, do you remember, Andrei, that after George Osborne had retired as Chancellor, you were the guest editor of Research Fortnight, and you asked me if I could get an interview with him. And we did, and I sat in on that interview. And you asked him why he was so supportive of science. Was it for economic reasons? And he said, no, I can say this now. That's because any advanced nation should value the importance of knowledge and discovery, which we thought was really good, actually.
It was very good, and especially important was that he said, I can say it now, because he was just resigned, because it's not very popular to support fundamental science when people ask for bread and circuses, essentially. But I always believe that we live in kind of a pyramid in a positive way. And the basic of this pyramid is fundamental research. And if we pull out this basic research, everything would crash immediately, not immediately, after a few decades. If you see, it's very nice to have LED projectors and computers and so on. Kill fundamental physics in the universities or semiconductor science, forget about any further projects, but in 2 decades people will forget how to make transistors because mistakes will appear in the current industrial processes and computers one in a sudden stop working. That's very important to remember. So someone has to do this.
One more quick question, I think, if we have one. Can't see one.
There is a lady over there.
Sorry, where? At the right? Oh, yes, yes. Go on.
I think someone else had a question over there. It might be a better one.
It's quite hard to see from here.
Thank you so much. I was just wondering if you think in time other forms of carbon will be discovered.
Ooh. In time, will other forms of carbon be discovered? Difficult
Why
question.
not? It's a proper scientific question. I think people suggested many other allotropes, so graphite, carbon nanotubes, buckyballs, graphene. It's all allotropes, so-called allotropes of carbon, and people have managed to at least theoretically create many other allotropes in computer simulations. There are also kind of experimental allotropes, Graphene. It's kind of graphene, but with big openings, big rings, and so on. So, yeah, those are under investigation now. Didn't come anything spectacular at the moment, but it's an active area of research.
So I think we should close because although we have run over a little bit, but we started late. I want to say thank you to the audience again for coming, but particular thank you to Andrei. It's quite normal, as we've seen today, for Nobel Prizes to be won at the end of your career. It was definitely not the end of Andrei's career, and he has probably published more highly cited papers since the Nobel Prize than those of us who are academics in the room collectively. And of course, he's also won an Ig Nobel. And I learned in conversation just before coming in here that he was at one time a paramedic as well on expeditions, amongst his many talents. So can I just say thank you, Andrei, for allowing us.
Thank you. Thank you. Thank you.